Hello all, welcome back to Electronic Devices and Circuits video lecture series. I am BVV Sachinarayana, Associate Professor in Department of ECE, Vishnu Institute of Technology, Bhimavaram. In unit number 3, Rectifiers and Filters, we already discussed about Introduction to RPS, Basic Rectifier Setup, Off-Wave Rectifier Operation and Waveforms, Center-Tapped Full-Wave Rectifier Operation and Waveforms, Bridge Rectifier. In this video, I am trying to derive the characteristics of off-wave rectifier such as average DC load current IDC, average DC load voltage VDC, RMS value of load current IRMS. Objectives. The objectives of this lecture are derivation for average DC load current IDC, derivation for average DC load voltage VDC, derivation for RMS value of load current IRMS. For each and every rectifier, there are 12 important characteristics. So in this lecture, I am trying to derive the first 3 characteristics. The first one is average DC load current. That is IDC or I average. The average or DC value of alternating current waveform can be obtained by using integration. To obtain the average value of an alternating current waveform, first determine the area under the curve over one complete cycle, that is from 0 to 2 pi, and dividing this with the base. That is 2 pi. So first let me draw the waveform of full wave rectifier output. So this is time axis and this is load current. So the output of half-wave rectifier is pulsating in nature. So positive half cycle there is a load current, negative half cycle no current, again positive half cycle there is a current, negative half cycle no current. So this is the load current of half-wave rectifier. Since the current is changes with respect to time, we need to calculate the average value, DC value. And if you calculate the average value for this waveform, we are getting, it is like this. This is IDC or I average. So as to calculate the average value, first calculate the area under the curve for one complete cycle. Means I'm assuming it is time axis, it is a omega t axis. So I'm considering radians, so that is 0 radians, pi radians and 2 pi radians. So from 0 to 2 pi, calculate the area under the curve. Okay. So here mathematically the current waveform for half wave rectifier can be described as IL equal to Im sin omega t per 0 less than or equal to omega t less than or equal to pi, and that IL is equal to 0 for pi less than or equal to omega t less than or equal to 2 pi. So where Im is the peak value of load current. So now by using this IL equation, we can easily calculate IDC. So our IDC or I average is equal to, so first find out the area under the curve using integration. So integral IL d omega t with limits 0 to 2 pi. So this is area under the curve for one complete cycle. So it must be divided with the base, that is 1 by 2 pi. So by solving this equation, we can easily obtain the average DC load current. So very clear, we can represent this one as 1 by 2 pi integral 0 to pi IL d omega t plus 1 by 2 pi integral pi to 2 pi IL d omega t. And from pi to 2 pi, the load current is equal to 0. So the second term, it becomes 0. So our IDC is equal to 1 by 2 pi integral 0 to pi IL d omega t. And we know that IL equal to Im sin omega t. Since the output waveform, it is sinusoidal in nature, so our IDC equal to 1 by 2 pi integral 0 to pi Im sin omega t d omega t. Then Im, it is the peak value of the load current, which is constant. So take it out. Take it out from the integration. So that is Im by 2 pi integral 0 to pi sin omega t d omega t. Then after apply the integration, IDC equal to Im by 2 pi integral sin omega t, it is minus cos omega t with limits 0 to pi. And if you apply the limits, then our IDC, it becomes Im by 2 pi into, so minus cos pi, it is equal to minus 1. So minus into minus, it is equal to plus 1. Cos 0 equal to 1. So IDC is equal to Im by 2 pi into 2. And this 2, it's cancelled out. So our IDC equal to, or I average equal to Im by pi. IDC equal to I average equal to Im by pi. That is the average value of the load current. So in the waveform, we can represent this one. So this IDC or I average equal to IM by pi, this line. Then IM is the peak value. That peak value we can calculate. So for that, draw the off-wave rectifier when the diode is forward biased. So here it is the off-wave rectifier with diode forward bias. So step down transformer and diode it is forward biased. So I'm representing with the forward resistance RF and the load resistance RL. So at the primary we are applying our AC signal, that is 230 volts, 50 Hz AC supply. Then the secondary winding resistance we can represent it as a RS. RS is the secondary winding resistance. And in this, across the secondary, we are getting a voltage. We are assuming it as a VM. That VM is the peak value of the AC voltage or secondary voltage. So because of this, some current is flowing through the circuit. So I'm assuming that current as peak current IM. So from this equivalent circuit, we can easily calculate IM. So if you apply the KVL to the output circuit, then VM equal to IMRS plus IMRF plus IMRL. So all these are in series and a peak current is flowing through all these things. So VM equal to IM, it is common, RS plus RF plus RL. So from this, the peak current IM equal to VM by RS plus RF plus RL, where RS is the secondary winding internal resistance, RF is the diode forward resistance, and RL is the load resistance. VM is the peak value of input AC signal or the peak value of the secondary. Then the second parameter is average DC load voltage. So that is VDC or EDC. In some textbooks, it is represented as EDC. Now we know that VDC is equal to the average current IDC into the load resistance RL. So we already calculated IDC. So this VDC equal to IM by pi I already calculated multiplied by RL. So this IM is also already calculated, that is VM by pi into RS plus RF plus RL into RL. So this VDC, it can be represented like this: VDC equal to VM by pi into RS plus RF by RL plus 1. Here RS and RF are very, very small. Those are the internal resistances. So we can neglect. Compared to RL, those two are very, very small. So we can neglect those two. Then the average DC load voltage VDC or V average is equal to Vm by pi. VDC or V average equal to Vm by pi. So the load voltage, if you sketch, suppose the load voltage or output voltage of a rectifier, it is proportional to the load current. This is the waveform. This is the waveform. For positive half cycle, there is a current, and negative half cycle, no current. Now, if you sketch the average value, this is the average value. This is VDC. That VDC equal to Vm by pi. Okay. So if you neglect RS and RF, if we neglect RS and RF, then only our VDC equal to Vm by pi. Suppose if RS and RF are finite, if RS and RF are not very small, negligible, those are finite, it's having some finite values, those values are given, suppose, then you cannot calculate VDC by using equation Vm by pi. For such cases, first calculate Im. From that Im, find IDC, then find VDC by using equation IDC into RL. Okay, so this is the best method to calculate. If you neglect RS and RF compared to RL, then only our VDC equal to Vm by pi. Otherwise, our VDC equal to IDC by RL, where that IDC equal to Im by pi, where Im equal to Vm by RS plus RF plus RL. That is the second characteristic. Then coming to the third characteristic is RMS value of load current. RMS value of load current, that is IRMS. So very clear, the output of half-wave rectifier consists of AC component. It consists of AC component. So in general, those AC values are expressed by using RMS. So with these RMS values, the magnitude of AC signal can be found out. Means I can say RMS values gives the magnitude of AC signal. So in our rectifier output, there is AC component. The magnitude of that AC can be obtained by using these RMS values. So RMS means root mean means average and square. So the RMS values can be easily obtained. In reverse, we are calculating. Okay, first squaring, then find out the mean or average, then apply square root, then we are getting RMS values. So I'm trying to calculate this RMS value of load current. So that IRMS equal to, So I wanted to calculate the RMS value of load current. So first take IL. So first one it is squaring. So square IL square. Then find out mean or average. So alternating current waveform average value can be calculated by using integration. So integrate over one complete cycle, that is integral 0 to 2 pi and d omega t, and total it is divided with the base, so that is 2 pi. Then apply square root, so which gives the RMS value of the load current. And we know that our IL equal to Im sin omega t. So IRMS equal to square root of 1 by 2 pi integral 0 to 2 pi Im sin omega t d omega t. Im sin omega t whole square into d omega t. And since it's a half wave rectifier, from pi to 2 pi no load current flows, this IRMS becomes 1 by 2 pi integral 0 to pi Im sin omega t whole square d omega t. Since the current is 0 from pi to 2 pi, then apply the integration. So IRMS is equal to square root of, so Im square it is constant, take it out, so Im square by 2 pi integral 0 to pi sin square omega t dt d omega t. So integral sin omega t, which is equal to 1 minus cos omega t by 2. So IRMS equal to square root of Im square by 2 pi into 1 minus cos 2 omega t by 2 with limits 0 to pi. And after applying the limits, IRMS equal to square root of Im square by 2 pi into pi by 2. So then this pi it's cancelled out. So it is Im square by 4, that equal to Im by 2. IRMS equal to Im by 2. That is the magnitude of AC component, AC signal present in the half wave rectifier output. Coming to the summary, in this lecture we have learned the following: derivation for average DC load current, derivation for average DC load voltage, derivation for RMS value of load current for half wave rectifier. In the next lecture, I will derive the expressions for DC output power, AC input power supplied, and efficiency. Thank you. Thank you all.